This is our DNA project by Cade Fuller.
Andrew Marmo, and Emmanuel Dean, but unfortunately he couldn't be here on this fine evening, but he's with us in spirit.
This is made out of DNA structure, replication, transcription, and translation.
Oh, yeah. Alright, so as you can see in this drawing, we have the full DNA structure. We have the 5-carbon sugars, the deoxyribose, the phosphate group, as you can see, is marked PO4, the anti-parallel backbones that go 3' to 5' and 5' to 3'. We also have thymine, cytosine, adenine, and guanine. The pyridines and pyrimidines, which are all bases, complementary bases. Alright, so right here we have the double helix. The double helix is like the map of the DNA. As you can see, the DNA acts like rungs of a ladder.
Rosalind took X-ray diffraction photographs that suggested that DNA was arranged as a tightly coiled hexagon. Watson and Crick, using Franklin's X-ray patterns, they figured out that the structure of DNA in 1962, they received a Nobel Prize. Now we're going to talk about hydrogen bonds and covalent bonds. Hydrogen bonds are much weaker than covalent bonds. They are easily detached, and covalent bonds are sturdy and they connect and join each other. They are found in the DNA.
Alright, so next we're going to talk about the anti-parallel backbones. As you can see, the anti-parallel backbones go from 3' to 5', and on the opposite side, go 5' to 3'. Nucleotides are composed of sugars, a deoxyribose, a phosphate group, and a nitrogenous base. Alright, so these are the complementary bases. You have the pyrimidines, which are thymine and cytosine, and the purines, which are adenine and guanine. The pyrimidines are smaller, while the purines are larger, and these all make up the complementary bases. Alright, so when the DNA replication occurs is during the S phase of the cycle.
Where it happens is in the nucleus. DNA stays in the middle of the nucleus, and this is going to help it come out of the nucleus and become DNA.
Alright, so in this picture you can see how helicase goes up through the bonds and breaks them all apart. It always goes 3 to 5.
As you can see, the helicase has started to break the hydrogen bonds. It is tearing it up from 3 to 5. To hold it apart, the SSB proteins will keep it apart so the DNA doesn't close. The proteins floating around are free nucleotides, and they will be collected to make DNA.
DNA polymerase gathers all the free nucleotides and functions as a matchmaker.
It will go up the leading strand and come down the lagging strand. It always goes 3 to 5 and 5 to 3.
In this picture, it shows that the RNA primase follows up behind the helicase and works 3 to 5. Also, the ligase is what glues together the Okazaki fragments that are caused in the lagging strand.
The process of transcription is turning DNA into RNA.
In transcription, messenger RNA is single-stranded, smaller and shorter, only codes for one gene, and does not have thymine. Instead, it has uracil.
In translation, we are making the messenger RNAs, so we need to take out the extrons and keep in the introns. To start off, we're going to keep the cap so it knows where to go, and the AA tail.
Also, it'll have a poly A tail.
So this is when the messenger RNA completes the other side of the DNA. It matches up with everything and becomes the new protein.
Elfin.